Hey everyone, hope you guys are doing well. So, this session is going to be really important and really, I believe, is one of its kind in YouTube. I don't think anyone has ever done this sort of implementation on YouTube. So, the session is going to be full of uh, high value content. So, buckle up for something really amazing. So, the topic for today is disaster recovery plan. So, any production grade system must have a disaster recovery mechanism in place because disasters are inevitable. No matter how robust your architecture is, no matter how strong your infrastructure is, some days you gotta have those rainy days where your infrastructure will fail. That could be due to some hardware failure, that could be some natural calamity, or that could be due to any uh, cyber security attack or infiltration. So you gotta have some sort of recovery plan and disaster recovery plan in place so that uh, you are not found wanting when it really matters, because it's tough to uh, build any application that has that actually has real users. And if you have any application that has real users, that has gained the trust of the users, then you would not want to shatter that. And disaster, if you don't have a proper disaster recovery plan, this could be a trust breaker between you and your user. In this day and age, downtime is an absolute crime, and it's a sin. So whenever we talk about disaster recovery plan, what we do is we first do proper risk assessment. So what we do is we sit together, our business team as well as our tech team sit together, and we discuss like what are the potential risks, and we discuss like what are the likelihood of those actually hitting our business. And once we discuss those risks, we then perform the business impact analysis, like what kind of impact it can have on our business and our system and our application. And then based on that, we determine the RTO and RPO. So RTO and RPO are two really important terms which are widely used in disaster recovery implementations. And basically the whole disaster recovery plan any business use revolve around these two terms. So basically, RTO means recovery time objective, and RPO means recovery point objective. So recovery time objective means how much time your application takes to fully restore from a disaster. That is called RTO. I'm gonna show you a diagram in a while, so just bear with me. And RPO means, let's suppose a disaster happens. So you may have a backup of your database or your systems. So your application is now down, so you can restore your application to a point in time in the past, right? So if you take more frequent backups, say that you are taking backups every 15 minutes, that means that a disaster happens right now, then that means you have a 15-minute old backup and you can go back to that backup. So that means your RPO is 15 minutes, right? And if a disaster happens now, how fast can you bring the whole system up? Can you bring the system up in 5 minutes? Can you bring the system up in 10 minutes? Or it takes 30 minutes or an hour? So that is what we call RTO. So we want to keep RTO and RPO really small, but it comes with a cost, and we gotta have a balance between the cost and the recovery time. Now that we discussed the RTO and RPO, this is the perfect time to discuss the DR strategies that companies implement based on that RTO and RPO. Whatever strategy that we use, it depends on the RTO and RPO. If the RTO and RPO is high, we can implement something as simple as backup and restore. But if the RTO and RPO is less, then we have to implement something from these three, one of these three. So in the backup and restore method, what we do is, as the name suggests, we just take the backup of our data, and in case of any disaster, we create the database, or if it's in any volume that is attached to EC2 instance or any virtual machine, we just bring back the system using that backup. So it has no cost associated other than the storage of those backups. So this is the cheapest of all, but it takes time to restore. So it has, for a complex system, it can have a downtime of an hour or so, and that means it takes quite a bit of time, and you will be ready to lose that much of data. Then the second method, we call it pilot light. In this method, what we do is we keep the database live. We don't keep any other server or EC2 instances running. In this case, we have the database running, and in case of any disaster, we spin up EC2 instances and virtual machines, deploy our application there, and then connect that with the live database, which we have already deployed there. So in this case, because the database is already running, so it has some cost associated, but because the database is running already, the downtime is we don't face that much of downtime. The downtime is in 10 minutes to 30 minutes. So that much of data we're gonna lose. Then comes the warm standby. In the warm standby, what we do is we have the database running, we have the application running in another region, but we're not serving the traffic from that region. It's a scaled down version of our application running in another region, and in case of any disaster, we scale the infrastructure up, and then we do the failover at the DNS level. So this is what we call warm standby. Then comes the active. In this method, what we do is we serve our application from multiple regions, and even if one region goes down, we have another region serving our application. So that is why, because we are serving from multiple regions, that is why we say active. This is the most expensive one, but it has no downtime. After this is the one which is most widely used. It has the RTO and RPO in few minutes, and this is the second most expensive one. These two are generally implemented in most of the organization. This is implemented in systems which are really critical in nature, like banks or financial institutions or healthcare related applications. For normal applications, these two are widely used. So this is how we implement a backup and restore implementation. This is the main region in which our whole infrastructure is running. We have our EC2 instance, we have the RDS, and what we do is we take the backups of our EBS or the EC2 instances, and we keep the snapshot in another region, right? And we don't have any EC2 instances running here. All we have is the snapshot of our databases and other stateful application or other EBS volume which we may have, and we store them in another region. So we have the database snapshots, volumes, and other things in this region. And let's suppose this whole region goes down. What we do is we spin up these EC2 instances, and we then connect them to these, and then we spin up the RDS using the RDS database snapshot, and then we connect this EC2 instance to this RDS, and this is how we bring our application up. But again, since we are spinning up things from scratch, this will take time. As we discussed, this is the slowest of all, but the cheapest of all. Then comes the pilot light. What we do is, in this case, we keep the database running in multiple regions. As we can see, this is our primary region. and this is serving the traffic. As you can see from the Route 53, this is the active region. This is hitting this load balancer, and this load balancer is then routing the traffic to these servers. And we have this database here. This database is being replicated in another region here as well. So if this whole region goes down, here you can see that we don't have any EC2 instances running here. Our application is not running in this region at all. All we have is the database being replicated here. So if this whole region goes down, we bring the application up in this region, and then we do the failover from the Route 53, and then this region starts serving the traffic. So because we have the database running here, so the time which is the time to bring this whole system up will be relatively smaller compared to the backup and restore. So this is how we implement the pilot light. Because the database is running here, so it has a cost associated with this method as well. Then comes the warm standby strategy. In this method, what we do is we have two regions, and in one of the regions we have our whole application running, and in another region we have the application running, but we are not serving the traffic. As you can see that we have the whole application running in multiple regions. We have the load balancer here in multiple regions. We have the EC2 instances in both regions, and we have the RDS or the database in both the regions. So any data in this region is being replicated to this region as well. But we are not serving the traffic from this region. The only difference here is that between these two regions is that the servers here are scaled down, or the minimum number of instances. Like if in this region we are maybe, let's say that we are running 5 EC2 instances, but in this region, the warm standby region or the warm region, we have maybe 1 or 2 EC2 instances running. And let's suppose that this whole region goes down, then in that case we scale up these EC2 instances to the required number of EC2 servers, and then we do the failover from the Route 53, and then this region starts serving the traffic. Because we have the database running here, we have these EC2 instances running here, we have the load balancer running here. Basically we have a bare minimum version of our whole application running in this region. So this is expensive, but the downtime is really small, in few minutes. So this is the advantage of warm standby. Then comes the active implementation, which is the most expensive one, but it gives the downtime is zero downtime, because we are serving the traffic from multiple regions. So we have the application running in 2 regions, as you can see, and from the Route 53 we are splitting the traffic, or we are serving the traffic based on actually doing the load balancing here at the Route 53 level. And this way, even if this region goes down, we'll still have this region serving the traffic. So what I'm going to be doing is I'll explain this whole setup, and then because I have the practical implementation of this after this whole demonstration, so let me first explain this architecture. Let's first focus on this side of the architecture. Here we have RDS running in 2 availability zones. Then we have the applications running in multiple availabilities, multiple subnets in these 2 availability zones, and then we have the public subnet in which we have the load balancer. So what we have done is we have spin up multiple instances of RDS, and when you spin up multiple instances of RDS, one of them will be writer instance and one of them will be reader instance. So this particular instance will be used for any write operations, and this particular instance will be used for any read operation, right? So because this is an active implementation, so what you have to do is, what AWS internally does is, whenever you perform any write operations here, it will be automatically synced to the database in this region. This is what we call cross-region replication. AWS does this whole thing internally, and because you might be thinking that, okay, we have one reader here, one writer here, so what happens to any write request from this region, right? That's a valid question, because in this whole setup we have only got one writer. This is also a reader instance, this is also a reader instance, this is also a reader instance, right? So the applications running in this region, if they have to perform any write operations, they have to talk to this instance which is in this region, right? These instances are only reader instances. They can read from these instances. This way they can have low latency, but for the write operations they have to talk to this EC2 instance. So what we have done is, we have stored the database credentials in this secret manager in both the regions, and because we have one writer instance, so in the secret manager what we have done is, writer instance endpoint store in both these regions. Okay, so the applications running in these EC2 instances will fetch that from this secret manager using this IAM role, and then they will be able to point to this writer instance. For the read operations, they can access the reader instance in that particular region, because this region has a reader instance here, this region has two reader instances. So for the reader instance there is no problem, but for the writer instance this may change, because let's assume this region goes down. In that case this whole writer instance goes down, right? So what it does is, the moment this region goes down, we have to fail over the database, and when we do the failover, one of these reader instance will become a writer instance. So when one of these instance becomes writer instance, we have to update the writer instance endpoint in this secret manager, right? So that these EC2 instances running in this region could point to the correct writer instance. So this is something which is really crucial, because with RDS RDS does not have this automatic failover and automatic update of the writer endpoint. This is something which we have to manage. With DynamoDB, this is something relatively simple, but with RDS this is something which we have to manage. And another thing here, let's suppose that because this is an active region, in this EC2 instance, or the application running in this EC2 instance, they store media files or objects in S3 bucket, this S3 bucket. So to ensure that the data stored in these EC2 instances are available even if this whole region goes down, we have to enable cross-region replication for this S3 bucket, so that if the S3 bucket goes down, we have the data stored here, and this gives us this redundancy. So this is a really robust implementation. We are accessing the static files through the CDN, and rest of the request will go through the load balancer. So we're going to implement this setup using Terraform. We do have the application code as well, and the only thing which I don't have is I don't have any domain, so I probably might not be able to implement the Route 53, but rest of the things will be implemented as we have discussed in this whole setup. This whole setup can be implemented as an active and warm standby. So if we let the traffic to flow to both these regions, then it will act as a active. But if you only allow traffic to one region and scale the EC2 instance in the other region down, then that will act as a warm standby. So that's the only difference. So let's jump right into the Terraform code. I'll try to explain the Terraform code there, and then once we are done with that, then I'll deploy the Terraform code, and then we will see the actual implementation and things in action. So let's jump right into the code. Let me explain the Terraform code. So we have two regions. One is the primary region and one is the secondary region. So this one is for the primary region, and in this main.tf file, let's start from the top. We created the primary VPC, and this is the server, and in this VPC we created two public subnets and two private subnets for the backend application and two private subnets for the database, right? And then we configured the regular VPC setup, like setting up the internet gateway, setting up the route tables, and setting up the NAT gateways, because our application is in private subnet, so it needs access to application for downloading the packages and even cloning the repository. And for that reason, we have to configure NAT gateway as well, right? So that is why this NAT gateway here. This is related to the VPC, and then the security group. We're allowing port 80, port 500. On this port, our application runs. On this port, we are allowing the load balancer. That is why port 80. And then internally, our application runs on port 5000. Then this is for HTTPS. We don't have HTTPS, but you can use this port if you use any certificate manager like ACM or Let's Encrypt. You can use then this port. This is for the database, and this port accepts requests from these two server block. This is for the primary. This is server of the primary VPC, and this is the server of the secondary VPC. We need to allow from both these server ranges, because let me show you. Because in our secondary region we have application deployed here, so it needs to talk to this router instance, right? So that is why we have to have both the VPCs servers in this server block. And then to allow SSH, we have port 22, and this is related to the security group. And then what we have done is we have created an IAM policy, and then the actions that are allowed is allowed S3: get object, put object, delete object, and list object, and then access to the secret manager. And then we attach this IAM policy to this IAM role, and because our EC2 instances need access to the S3 bucket as well as the secret manager, for that reason, let me zoom it, our EC2 instances need access to the S3 bucket as well as the secret manager. That is why we have given these permissions here in this IAM policy, and then we have attached this to the instance profile. And then the really important thing to understand here is we have created a RDS global cluster, and then in this cluster we created two primary clusters. There were two cluster. One is the primary cluster that is in the primary region. Let me show you the diagram. So this whole is the global cluster. This whole thing is the global cluster, and then in this cluster we created two more clusters. This is the primary cluster, and then this is the secondary cluster. So that is what we have done. Primary cluster. In this primary cluster we have a primary instance 1 and primary instance 2. So that is what we have done here. We have this cluster, global cluster. In this global cluster we have this primary instance a primary cluster, and inside this primary cluster we have the primary instance 1 and primary instance 2, and we have done the exact same thing here as well in the secondary region. I'm going to show you the code. Then we have created a launch template, and in the launch template what we have done is we have actually pushed this code to the GitHub, and from GitHub it is pulling the this repo in this user data, and then it is going into this backend directory here. This is where our backend application code is, and then it is creating the necessary environment variables, and then it is starting the application. So this is what we have done in this launch template, and then using this launch template we are creating this auto scaling group, and we are saying we need desired capacity is 2, maximum capacity is 5, and minimum capacity is 2. So this is how we are creating our EC2 instances using those launch templates. So we are creating these EC2 instances in both the regions using these launch template. So and then application load balancer as well. So then we created the application load balancer, and this load balancer is listening on port 80 and targeting on port 500, port 5000. So this is related to the primary region, and then in the secondary region we have done exact same VPC setup, and then I'm not going to discuss the VPC and the security group. That is exactly same as primary region. The difference here is we created this secondary database cluster, which I was discussing just now, the secondary cluster, and then in this secondary cluster we have created a secondary instance 1 and secondary instance 2. So this I'm talking about this one. We have created the secondary cluster here, and then the secondary instance 1 and secondary instance 2. Then exactly as we have done in the primary, we created this launch template. In this we specified the user data, and then we clone our repository, and then change the directory to the backend, then set up the environment variables, and then we start our application. This is how, and then we have this load auto scaling group, and then we have the application load balancer. This application load balancer was, so this is related to the secondary group. And then let's talk about the S3 bucket. So we created 2 buckets, primary bucket and then secondary bucket, and then what we have done is we have enabled the replication, and this is related to the policies required for the replication. So this is, we have created these 2 buckets, and then we gave the permission so that the replication could take place from the primary to the secondary. So that is what we have done in this code. And then in the CloudFront, what we have done is we have created a CloudFront distribution, and then in this distribution we have given 2 origins. The one origin is the primary bucket, and the other one is the secondary bucket, and then the failover criteria is these codes. So if we get any of these codes, then the CDN will switch from this origin to this origin. So this is how we have implemented the CloudFront, so that the CloudFront could switch between the 2 S3 buckets. And then comes the secret. So what we are doing is we are storing the database details, the database username, database password, and then the primary cluster endpoint, secondary cluster endpoint, DB name, and then the CloudFront URL, and then the main S3 bucket and the secondary S3 bucket. So this one is the main S3 bucket where all the writes happen, and this one is the secondary S3 bucket. We have stored all this in this secret, and also we have enabled the replication because we need access to this secret from both the regions. So we are creating in this region, this region, and then it will automatically replicate it to this region, so that our EC2 instances in this region could access the secrets from here. So this is related to the secrets. And then I have created the bastion host, 2 bastion hosts, these 2 in both the regions, so that in case if we need to SSH into these, because these are in private subnet, so we cannot access these. So what we do is we log into these bastion hosts, and then from there we jump into these EC2 instances, and then debug if in case we need to debug anything. And then I believe we are done. Okay, so Route 53 as well. So right now I don't have any domain. That is why I have commented out the whole code related to Route 53. But if you guys have any domain, what you can do is you can uncomment this code, add your domain here, and then let this code run. It will automatically configure the whole Route 53 setup as we have discussed here. So right now I don't have any domain, so I have commented out this code. I'll try to switch between these 2 load balancers manually. And then I think we're done with the infrastructure, and I've already so it also generates the SSH key here. So if needed, we can make use of this SSH key to log into those bastion hosts. So because this thing actually takes a bit of time, so I've already applied this code, and it has already produced these outputs for me. Let me show you the output. Actually, I forgot to discuss the outputs. Actually, first we need to show you the variables.tf. In the variables.tf, we are specifying these variables. This is the project name, this is the primary region, this is the secondary region, DB name, DB username, DB password, instance type, AMI primary, AMI secondary, and then the app secret name. So these are the variables we are passing to this Terraform code. And then in the output we are getting the primary ALV DNS and the secondary ALV DNS. We will need these 2 so that we could connect to these 2 regions, right? Our application actually. So now let's jump right into the backend code and discuss the backend code. In the backend code, all it needs is 2 variables: the region in which the application is deployed, and then the secret name. So based on these 2, what it does is it fetches all the details from the respective region. If it is in US East 1, it will fetch from US East 1. If it is in US East 2, it will fetch from US East 2, because we have created the secrets in both regions. So applications can fetch from their respective regions. So that is what we have done. And then related to if the application is in US East 1, it will connect to a primary cluster endpoint. This one, if these 2 applications will connect to, for the read operation, it will connect to this write operations, and for the read operations, it will connect to this reader instance. And this particular thing is taken care of by Aurora itself. We don't have to do anything. We just need to specify the primary cluster endpoint. And if the region is not US East 1, that means if the region is US East 2, it will make use of the DB secondary cluster endpoint, and it will talk to using the secondary cluster endpoint. If the request is read request, then they will be served from that region's instances. If the request is write request, then they will be forwarded to the writer instance in the other region, and that particular thing is also taken care of by Aurora. We don't have to do anything at all. So, and this particular thing works because let me show you. Hang on a minute. In the secondary cluster, while creating the secondary cluster, we have enabled global write forwarding. So that is why any write operation from this region will be forwarded to this writer instance, and that is done by Aurora internally. We don't have to do anything, and this actually makes this whole setup active. So this is how we have the application code, and rest of the logic is there's not much we need to discuss. And the beauty about this particular code is, and this particular setup, is that in normal circumstances both the regions will serve traffic and it will work seamlessly. But let's suppose that if this region fails at the Route 53 level, what we'll do is we will disconnect it, and then we will fail over the database. So the moment we do the failover, one of these will become the writer instance, and we will then update the secret in the secrets. Here in the secrets we will update the primary cluster endpoint, and when we update this, our application will directly pick that. We don't have to change anything. All we have to do is to just do the failover and update this value, and this is how this whole setup will work. So I have already deployed this whole infrastructure, and also the application is live. All you have to do is to do Terraform apply from this infra directories. Because our Terraform code is here, we have to do this, and then it will provision the whole infrastructure, and you will get the primary LBDNS and then the secondary LBDNS. So what we're going to do now is we're going to open this particular, because this is our front end and we need to make use of these application and to talk to the backend, we need to open this index.html in the browser. And because we have got these two load balancer URLs, these two URLs, so what I'm going to do is I'm going to copy them, and I've actually copied them. Don't worry if I'm not copying again, I've already done that, and paste it here. So first I'll try to connect to the primary ALB. This one I'm trying to connect to this one, and yeah, I've actually connected to this one. And let's open this in the browser. As you can see, I've actually tried to test this one, so it was working properly. These are some of the images and videos I've uploaded. Let's try to upload another one. Right, I'm connected to the primary, so let's try to upload another image, a smaller one. So it is uploading. So you can see it has uploaded this image. So now what I'm going to do is I'm going to comment this one because I don't have any DNS, so that is why I could not use the Route 53. Otherwise we could have automated this whole thing as well. So now I'm trying to connect to the secondary, this load balancer. So let's save this one, and then let's refresh. So you can see that it is now this serving the whole content from this load balancer. So I'm gonna try to upload this image just to test that the upload thing is working from both ALBs or both regions. See, it has uploaded this image. So this proves that this is an active setup. Both the regions are working properly, and this can be configured as a passive setup. All you have to do is to disconnect this one while configuring the Route 53 and scale these servers down, and only scale them up and connect if in case of failover. So this is how we implement a 3-tier fully functional production grade disaster recovery mechanism, which can be served as both active and active passive. I think this is one of its kind on YouTube. No one has gone into so much detail and so much depth, because it involves quite a decent amount of cost as well to spin up multiple RDS instances, multiple EC2 instances, and this whole set of cost quite a decent amount. So I hope you guys will love this content, share this content, and I hope that you guys can practice this on your side as well.